In the spirit of Halloween, we're going to talk about some really scary explosions today. So scary that, although they're very rare, if they happen to beam towards the Earth, that would be it. That would be the end of the civilization. So we're going to focus our lecture today on a special type of explosions that we call gamma ray bursts, or GRBs for short. Those explosions are unique in the sense that they don't seem to be symmetric. They don't seem to emit their energy and the radiation uniformly in all around the entire space, but rather beam it in the form of a jet towards a specific direction. And that has a lot of implications about the stars that die, what's going on, really, that produces this weird gamma ray burst explosions. So let's talk about history a little bit. Why do we call them gamma ray bursts? Yes, you want to dim the lights a little bit? Okay. Better? There? More? Good? All right.
Those can be turned off entirely.
Those?
Yeah.
Okay. All right, thank you. So, gamma ray bursts. The first two words in the definition of gamma ray bursts, of these stellar explosions, is gamma rays. Now, some of you may already know that gamma rays are the most energetic of radiation out there. As you know, light is split into wavelengths. So we go all the way from the radio waves, which is what we're using for our daily communication, radio, television, so on and so forth, which is totally harmless. Then we go to the infrared. Then we go to the optical, which is what we see right now with what our eyes are sensitive to. And then there is more energetic radiation, the ultraviolet, X-rays, which is what we use to actually do X-ray scans of our body and see if there's something wrong or if we broke a bone or something. And then as you go up the energy scale, you get to the gamma rays, which are the most energetic photons, the most energetic light that we have out there. And a unique characteristic of these gamma ray burst explosions is that they're very strongly radiating in the gamma rays. So that came as a surprise because those need to be really, really energetic explosions, more than typical supernovae, to radiate in such energetic light like gamma rays. So in order for us to be able to detect them, we have to build telescopes that are sensitive to capturing gamma rays. As a lot of you may have used optical telescopes in your homes to look at the moons of Saturn, of Jupiter, the rings of Saturn, and other celestial objects, those are things that are sensitive to the optical radiation. We built telescopes, very expensive telescopes, that are sensitive to different parts of the radiation, like the radio waves, or X-rays, or the gamma rays. And the reason for that is, it's going back to one of the first things I said in the beginning of this lecture series, is all we have is light to understand what's going on in this really, really distant, weird object. So we want to capture as much information from light as possible. So it's really wise to utilize and to capitalize on every single photon we can get across the spectrum. So we built dishes, like large radio telescopes, that are mounted in valleys, like Puerto Rico, and the Arecibo telescope, for example, which are looking at the universe in the radio waves. But then we also built X-ray and gamma ray telescopes, just like the Fermi, which is the same name as my fellowship, the Fermi Gamma Ray Observatory, which unfortunately, or fortunately I would say, it's very fortunate, the fact that gamma rays do not enter the atmosphere, it's a very fortunate event, and the reason why we're alive today. So the atmosphere is a shield to this kind of energetic radiation. However, if we want to observe things in the gamma rays, that means we have to go above the atmosphere. So we have to build orbital telescopes, which is what this Fermi Gamma Ray Observatory is, that go above, that go to space, there's no atmosphere, and they can clearly look at the gamma ray universe, and the X-ray universe, for that matter. So we built those, but guess what? Well before governments funded scientific efforts to build those for astrophysics, they built those for defense-related stuff. So back in the Cold War era, and that's an interesting story, the Soviets, the Reds, they were doing tests on space, and they were doing nuclear tests on space. And suddenly, some for the United States of the American satellites, Star Wars project, I think was the name, they started to capture gamma ray signals that were in orbit, and started to capture gamma ray signals. And the initial speculation was that a lot of these gamma ray signals was due to nuclear tests done by the Russians. Well, it turns out that when they looked closer to the source, although it was really hard to locate the source, of this gamma ray influx, they figured out that it comes from the outer space. So that's really when gamma rays were discovered. They were discovered back in the Cold War days. And initially, they were thought to be nuclear tests by the Russians. So it turns out they're not nuclear tests by the Russians. We see them across the universe in every direction you're going to look, northern hemisphere, southern hemisphere. You're going to find gamma ray bursts. And we believe that the energy of this gamma ray burst is expelled and radiated in narrow jets. And the question is, what are they? That's always what we theoretical astrophysicists want to answer. So what are these things? And there's two competing scenarios. The one that's more relevant to the class, I will discuss the other one as well, but the one that's more relevant to the class in terms of supernova explosions, cosmic catastrophes, is the potentially mark the birth of the black hole or a magnetar. Have you heard the term magnetar before? People that attend the lectures frequently, they probably have. So magnetars are newly born neutron stars that have really, really high magnetic fields. We're talking 10 to the 14 times higher than the magnetic field you find on the surface of the Earth. 1 to 14 zeros. Really strong magnetic fields on the surface. And we call them magnetars. They're basically neutron stars, highly magnetized neutron stars. And this is what gamma ray bursts look like if we capture the gamma ray. So this is the gamma ray for the gamma ray observatory. This is how the gamma ray picture of a galaxy looks like. And that blip right here, that bright little spot, was not there before. And it was discovered as a transient. So it was captured by this telescope. This is the gamma ray burst. Now there's, of course, other gamma ray sources in the universe that are not transients. A lot of energetic centers of galaxies, or AGNs, as we call them, active galactic nuclei, they emit a lot of gamma rays as well. So some of those red spots you see here as black spots would be AGNs, active galactic nuclei. There's also novae that occasionally will produce X-rays and gamma rays, but those are transients. But all in all, we care about the transient nature of this gamma ray burst. And this is an example of what it looks like. Now, we do have to give credit to the people that built these telescopes, because it's extremely hard to build instruments that can capture those gamma rays. The technical detail, the engineering detail that goes behind building these is spectacular. So what does a gamma ray burst look like, or what the light curve, the evolution of light intensity of a gamma ray burst look like? Well, I will tell you later that there's really two types of gamma ray bursts, as I mentioned before. And the way we split them is the duration of the gamma ray burst. So some of them are long duration gamma ray bursts that last about 30 seconds, half a minute, while others are way shorter, short duration gamma ray bursts. Now we're going to focus more on the long duration ones, again because they're related to stellar death. So for those, what we see with our telescopes is an energetic flash of gamma rays that lasts for about 30 seconds. And this is how it looks like. If you were this is the 30-second period. Within these 30 seconds, you see this burst that does all this really weird up and down behavior. So light basically flickers. The gamma ray flux, the gamma ray luminosity that you see within those 30 seconds is highly variable. This is how it looks like. It does have a few features that you can start talking about. There's obviously a peak that peak right here, the luminosity got into a higher level. And maybe you can just, looking at how long this lasts, those individual peaks or flickers, they last thousandth of a second sometimes. So that goes back to how important technology is for us being able to accurately capture these events and study them. We have to collect these gamma ray photons in really high frequency to be able to resolve this time. 10 to the minus 3 of a thousandth of a second. Now this map, when we look at features in a light curve, sometimes in astrophysics, since those are related to the speed of light, and the speed of light travels with a certain speed, which we know, and they have characteristic time scales. So the time scale of this peak is a thousandth of a second. We can relate that back to a scale. It's a really easy equation. It's basically velocity equals distance over time. So we solve for distance. The velocity, the speed is the speed of light. The time is this duration. And then we get a characteristic scale. And if you do that, and if you convert those numbers to the scale, we get something in the order of a few kilometers. It's about the size of downtown Chicago, which is the same typical size that we've been discussing. It's relevant. The scale is relevant to the sizes of neutron stars or black holes. So maybe that's the first hint, that we have to deal with scales that small in the center of stars are collapsing. But again, we still have to understand not just the big features here and why they lasted as long, but we have to understand the entire behavior. Why it flickers like that? What's going on in detail? Now, one of the biggest problems that we had before technology got better and better was that it was really hard to focus these gamma rays. So we got gamma ray fluxes before this Fermi telescope actually before it came along, and we didn't know where they come from. We couldn't locate the source of gamma rays. And that, for a long time, was a major problem because people started saying, well, maybe it's just something that happens to the solar system, some sort of, I don't know, solar flares or collisions of asteroids with the atmosphere of Jupiter or Saturn or something like that. Others said, well, maybe it's just galactic. But it turns out it's, those things happen all over the place, far, far away from us, thankfully, in the universe, in distant galaxies. So we won't be able to find that out once we build good enough technology and follow up using ground-based telescopes to actually locate the source of these things. So we didn't know the distance of these things for a long time because we couldn't localize where the source was. But the revolution on that happened in 1997 when we finally discovered the so-called gamma ray burst afterglow. So we were lucky enough for this event back in 1997 that after the first 30-second gamma ray emission, we saw an immediate decline, which lasted for a few days, in the other more friendly parts of the spectrum, in the optical and the X-rays, the optical especially. So we saw an optical afterglow source that kind of looked like a supernova light curve at the same location where this 30-second gamma ray burst was located. So we were able to finally make the connection and localize the source of gamma ray bursts. And we're finally we started seeing more and more and more of this type of events, followed by gamma ray afterglows. And now we have more information, finally. We didn't just have the short 30-second pulse, but we had optical to look at, and X-rays, and infrared. And we're able to collect more information because those emissions lasted for a more friendly timescale for us astronomers. They lasted for days instead of 30 seconds. So we're able to follow through. And we found that a lot of these bursts occur in really distant galaxies. Sometimes the galaxies are so far and so deep that we can't actually see the galaxy. We infer its presence, but so it looks like they happen in empty space. They don't really happen in empty space if you look through a telescope. They just happen really far and sometimes dim galaxies. So if you were to collect all the energy and the light that's produced by gamma ray bursts, you will find out that, and you measure how much light you get, that it is equivalent to about 1,000 or to 10,000 times the energy you get from a typical supernova explosion. So that was another surprise. Like, how is that possible? Why are these events so extravagantly energetic as compared to supernova, which we thought were already very energetic events? And the other weird thing about that finding was that if you were to use the very famous Einstein's formula, E equals mc squared, the conversion of energy to mass and vice versa, you came to the conclusion that you needed to convert the entire mass of a star, of a massive star, into energy to account for these explosions with gamma ray bursts. And that was a little weird because we knew that most of the energy in core collapse supernova, last lecture, is carried by the neutrinos. 99% of the energy is carried by the neutrinos. And it's only 1% that's stopped by radiation keeps the explosion, that aids the explosion. So how do you do that? Like, it's impossible to just convert the entire star into energy. Something else must be going on that we don't know about. But the flaw in this hypothesis was that we came down with this number, we came up with this number, assuming that those explosions radiate equally in all directions. So their energy, the radiation was kind of like uniformly split in three-dimensional space. It's uniform. Well, it turns out that if you actually take the same amount of energy and you focus it in narrow jets, in narrow outflows, you don't really need to convert the entire star's mass into energy. So people started thinking about the idea, well, maybe what really happens is that those explosions are highly beamed. They're jetted. They don't explode symmetrically. They explode kind of like a football. And those jets happen to be directed to us, and that's why we see them. Now, if those jets are not directed to us, we wouldn't see those gamma ray bursts. And as a matter of fact, we don't see most gamma ray bursts because they don't happen to be directed towards the Earth. So, and this is what this cartoon picture right here is trying to convey. You know, if you're looking at something that's signed symmetrically in space, no matter where you're looking at this from, you will get the same kind of amount of flux, of radiation, luminosity. However, if you look at something that's really highly beamed, you know, if you look at it through the pole, through the axis where the beam is directed towards, so you will see way more radiation than if you look at it through the equator, which, you know, it's going to be way dimmer from this side. And this is kind of like the difference between a light bulb, like the light bulb's up here in the ceiling, and my laser. You know, a light bulb up here in this room ceiling shines over the entire room, but this laser beam is really directed. And this is kind of like the difference between a regular supernova in terms of uniformity of direction and gamma ray bursts. Those are really high beams explosions. And as I said, they send matter when these things explode because the energy is so highly directed here. It's concentrated like a laser beam. The radiation is so strong that it can actually accelerate matter, the stellar matter of the star that actually explodes, to speeds that are really close to the speed of light. So these events, and that's a very important key point, are highly relativistic events. Those beams and the matter that's traveling away with those beams get to speeds really close to the speed of light. So, yes, sir?
And these beams, are they all moving the angular momentum?
Yeah, so we think angular momentum in magnetic fields is highly responsible for why they blow up this way. Yeah. Yes, sir?
Why are they focused instead of symmetric?
Well, exactly. That goes back to the question he asked, is the fact that you have some stars that are really highly rotating and have really strong magnetic fields. And magnetic fields tend to be aligned towards the axis of rotation. And that's magnetic forces in rotation causing the outflow to be a certain direction, preference in direction, whilst other stars will not rotate very fast, for example. So we think rotation is extremely important for these kind of explosions. But if we want to study them, and there's a lot of sophisticated computer codes, like Flash, but including a lot of special relativity, which deals with matter that travels with speeds close to the speed of light, to study gamma ray bursts. So people have built numerical algorithms and codes, 3 dimensions, to be able to study these things. These are not easy because you have an extra degree of complexity, which is the special theory of relativity, things moving at the speed of light, or close, very close to the speed of light. So, as I said, just because of the fact that they are directed, they really explode, the frequency, the rate of gamma ray explosions is really 100 times, about 100 times more than what we actually observe. Because we only get, you know, a few that happen to look or to be directed towards our solar system.
And what distances?
So the distances vary, but they're all very far away. They're further away distances. We're talking several of millions or billions of light years away. So from the light we get from these things takes billions of years, in some cases, to actually come to the Earth and be captured.
So it's within the observable universe.
It is, definitely, yeah. Everything is within the observable, yeah. So, yeah, those things, and actually, I think 4 years ago or 5 years ago, they discovered the gamma ray burst that was the furthest, the most distant object seen in the observable universe. It was about, if I remember well, 9 billion light years away, which means that that's when the universe was really young, because we know the age of the universe is 13.7 billion years, and that happened only, you know, 4 billion years or so after the Big Bang. So those, for some, I don't know if anything else broke that record ever since, but that was for a long time the longest astrophysical object we observed. It was a gamma ray burst. So those things, and there's a,
What's the angle of the beam? How wide is it?
so that will vary depending on how fast matter is moving, but which means that the fastest that matter is moving, the more direct, the more narrow the angle of the beam will be. But typically, it is 10 to 20 degrees, or even less. Sometimes 5 degrees from the axis, really narrow. And there's a little variance there depending on the energy of the gamma ray burst, but it's very narrow. Yeah. So, and one question that you all worry about is like, what if the gamma ray burst? And that's the Halloween kind of joke of the lecture. Is like, what if the gamma ray burst is really close to our solar system, and it happens to be being directed towards the Earth? Well, yeah, that's doomsday scenario. That would be very, very bad. The first thing that would happen is that the very energetic gamma rays produced by the gamma ray burst would impact the upper layer of the Earth's atmosphere, and would convert by several chemical reactions the oxygen and atmosphere oxygen and nitrogen molecules. And that would create a photochemical smog, kind of like an accelerated global warming deal, which would would thicken up the atmosphere, cover up the Earth, and darken the sky. And you would block radiation, you heat up the Earth, and you deplete the ozone layer. As you can understand, the Earth wouldn't be very hospitable to human beings anymore if that happened. However, we don't really have to worry about that much because those events are very rare. Most of them are very far away. And the possibility of actually having a beam to be directed towards the Earth, it's 1 in 100 million to 1 billion years. That would happen. So we're pretty good. We're fine. Don't worry.
Any evidence in that?
And they have to be also close. Well, they have to be within the galaxy to be of danger, which is another constraint. So this is, it's a very rare thing. Yes.
Any evidence in the geological record that it happened?
That's a good question. People have found evidence of other events in geological records, like asteroid impacts and energetic flares from the sun, from the solar circle. But I'm not sure they actually found, I don't know if they have found evidence of gamma ray bursts. I haven't heard anything on that topic. They definitely have found evidence of other astrophysical events. Yeah.
Just looking at your photo, just like, would it affect the whole Earth or just the side facing the?
Well, it would really affect the whole Earth. You can't just, the atmosphere mixes, the Earth rotates, so it will be over time. You can't just impact one side of the planet without having an impact on the other side of the planet.
This would be a very short course, though.
Yes, but the time scale over which the reactions are going to take place, and then the gas is going to start taking the sky is going to be a little longer, but it's going to be a slow but certain death. But it's not going to happen. So Let's don't worry about it. So let's talk. Yes.
So as the particles approach the speed of light, and nothing goes faster than the speed of light, the particles then begin to get larger in mass?
Yeah, I mean, you have all the effects of that special relativity predicts, the time dilation effects, the left contraction. That's why you have to put special physics and special treatment in the computer codes when you simulate this. Yeah, so you have all this kind of.
But aside from the gamma radiation, you would have, let's say, like a belt, like an asteroid belt of mass, because you're turning these particles into mass because you can't go faster than the speed of light.
No, not necessarily turning the particles to mass. The particles themselves, the gas itself, the matter itself, is accelerated at really close speed to the speed of light, right. But they're not going to. It's not like their effective mass going to influence anything dramatically. They're not going to make asteroids. They're just going to.
They can't go faster than the speed of light.
Yeah, they're going to be expanding to the point where they will start. Eventually, the density will be dropping, and you will have the effect of the expansion taking over at some point. So this acceleration of matter to the speed of light happens very early, but eventually, as the star explodes, it's a snowplow phase, as we call it. It expands and the speed drops of the matter and so on. So it's those first few moments that are.
I'm thinking more of the conversion of energy straight into mass, like the.
Which is the initial hypothesis, but it's not. Yeah, it's not really. So what we see after almost 20 years of gamma ray burst observations, and actually NASA's instruments like SWIFT, the SWIFT Observatory, has been instrumental in discovering gamma ray bursts, for example, in the Fermi telescope. We found a lot of these. We found enough numbers to actually start looking into properties and statistics. We're going to look into the zoology of gamma ray bursts. And luckily, the zoology of gamma ray bursts doesn't seem to be as multifaceted as the zoology of supernova, traditional supernova, I should say. So gamma ray bursts, as I said, have different durations. You have a lot of them that last about 30 seconds, and I'm talking about the gamma ray emission itself. Yet you have some others that are really, really, really much faster, less than 2 seconds, the short gamma ray bursts. So when you start seeing two populations of the same thing emerging after a lot of observations, then you have to start asking yourself, are these objects inherently different? Do they have inherently different nature, and why so? And what differentiates one from the other? Why are the durations different? Well, let's look at more statistics. The vast majority of gamma ray bursts are long duration gamma ray bursts, the ones that last about, usually around 30 seconds, definitely more than 2 seconds. And for these, we do see X-rays and UVs and optical afterglow, the afterglow light that I showed you. Also, very cool finding is that for the same location where these events take place, after the gamma ray burst, we see a supernova. We see usually a type 1c supernova explosion, a regular supernova explosion, which means that there could be association of these gamma ray bursts. And it turns out that there is association of these gamma ray bursts with type 1c specifically, a specific class of supernova. If you remember, type 1c supernovae are the ones that do not show neither hydrogen or helium in their spectrum. So those are stars for which you have stripped the hydrogen and helium outer skins of the onion. And now what you basically likely have is a carbon-oxygen material, which is the immediate layer inside helium. So you see a lot of type 1Cs associated with gamma ray bursts. And those events right here point to the fact that, to the direction that those are jet-induced deaths of massive, highly rotating stars. And they mark the births of black holes and neutron stars, or highly magnetized neutron stars, which we call magnetars. And this is what is called the collapsar model, from the word collapse and star. The collapsar model for gamma ray burst. One example is this 1998 discovery. So we have weird ways to name gamma ray bursts. Usually we put the GRB in front of it, and then we put some numbers. Usually the first two numbers, this is basically the date, 25 of April of 1998. This is when we discovered the gamma ray bursts. In terms of the short gamma ray bursts, they're only almost a third of the total population. For them, we don't see any afterglow in the optical and the X-rays, and we don't see any association with supernova, any obvious association with supernovae. So what are these? Obviously, different physical mechanisms involved here. One very popular idea is that those are mergers of neutron stars or neutron stars and black holes. Remember when I talked about type 1A supernova hanging out Black Company? One of the ideas of the progenitors of type 1A was white dwarf mergers. Well, in this case, we don't have white dwarf binary mergers. You have neutron stars that merge, or a neutron star with a black hole. And this is another example of one of these. So this is what it looks like. Don't be scared from scientific jargon, but this is what it looks like if you do the measurement. So here, we plot the duration in the x-axis, which is how long the gamma ray burst lasted. This is 1 second, this is 10 seconds, this is 100 seconds, this is 1,000. And those are like, a tenth of a second, a hundredth of a second, a thousandth of a second. And here's a number, how many bursts we find in this duration. And you can see the two populations emerging. Obviously, there is a big peak around here, around 30 seconds. It's the long duration gamma ray burst, but there's also a lower peak. A few occur down here, the very short ones. And then we can also start measuring their distances. Well, it turns out that if you do that, and that could be biased because we can't find, we can only find things we can see without telescopes. There could be more out there, we just can't see because we don't have strong enough telescopes. But with the telescopes we have, we find that the long duration gamma ray bursts tend to occur way further away from the Earth or from the galaxy than the short duration gamma ray bursts. And this is the one I was talking about before, this record breaker at redshift of 8, which translates to about 9 years ago.
What is the implication?
I'll get to that in a second. Yeah.
Is there any way of correcting this data? You have some estimate of what you're missing, so you might be able to correct this data?
It would be naive and wrong to try to correct data. That's one of the most dangerous things to do in observational astrophysics. You can make models and simulate implications of what you expect, but you can never present it as data. Data is data. That's it. That's what nature. That's what we can see.
The raw data.
Yeah, and you can. Maybe your assumption is wrong. So if your assumption is wrong, and you start correcting data with the wrong assumptions, then that's downhill from there. Yeah.
So the short durations are not beamed then?
The short durations are also beamed, yeah. And they also involve high degree of rotation because you have neutron stars rotating and merging. So the question is, what exactly the actual pair of compact objects is. Is a neutron star, some black hole? What's the difference? And there's a lot of, if those are, so if we're going to find out really what those are, if you remember what I told you like a few lectures ago about general relativity, very highly gravitating objects like neutron stars rotating with each other and merging would produce gravitational wave emission. Those gravitational waves, we should be able to detect them. With our next generation gravitational telescopes like LIGO, we'll start finding this, and we maybe find one that's in the same location as a short duration gamma ray burst. Well, that will nail the coffin. That will be the nail in the coffin. We'll say, yeah, we have more strong evidence that those short duration gamma ray actually relates back to neutron stars merging, or neutron stars black.
Do they also correlate with cosmic ray telescopes, the atmosphere showers that
well,
observed?
Indirectly, because cosmic rays are not optical. Just to give a little background, cosmic rays are not optical radiation. It's basically really highly energetic, protons, particles that impact the atmosphere. But sometimes you can have high energetic particles from the sun that impact the outer layer of the atmosphere that then convert into gamma rays. But those gamma rays that you get from that are not as energetic and don't have the same properties and duration as these things.
And they, moving it a little bit slower, 0.997, they would arrive later, in which time we've moved, right, and they miss us.
Yeah, so there will be some relativistic effects, but you will still get some flux.
Okay.
So, yeah, and then it becomes a question of deducing how fast they were moving, to figure out what the original state was. Yeah.
Why are the short ones closer to the Earth?
Well, when you see those numbers, they're closer as compared to the long ones. It doesn't mean they're in our immediate neighborhood or even in the galaxy. But that's a good question. We don't know. That's one of the things that people are trying to understand. We think it could be observational bias because we can't find, we have a certain technology to detect things, and those are really dim events. And maybe we can't find the ones that are further away because we just simply can't see them yet.
I mean, that's so short that you missed it.
Huh?
That's so short that you missed it.
Well, the shortness we can deal with because we have a technology to capture this 30-second beam right now. And actually, one of the tricks we do is we look at a big chunk of the sky simultaneously. So we take gamma ray pictures of a big portion of the sky, and then you can see more. But if you take pictures of smaller portions of the sky, it's very likely you will miss a lot. But if you take a big picture, which is a challenge technically, to simultaneously detect gamma rays, which is very hard, and have enough, big enough field of view to find the one. So
These are land-based instruments you're talking about now?
I'm sorry?
Are you talking about observations made from the Earth or from
From space.
satellite?
From space. From satellites. Yeah.
You can't see
I'm going
them.
to suggest that the distribution of the populations may also suggest that the objects that were prone to form along GRBs have thinned out over time, perhaps because the more massive stars destroyed themselves earlier in the history of the universe, leaving the second class, which are basically burned out remnants of other types of objects, later in the evolution of the universe. Is that a possible interpretation?
Yeah, definitely. Time evolution plays a role. There's a cause and effect here at some point. The thing is that if those are associated with binary star systems, that means that, and they're neutron stars firing each other, that means you also need massive stellar binary systems together to produce these. And then you can start talking about tax, because how long will it take for the two massive stars instead of one? So complexity really goes up. You can make those arguments, and those are the right way to think about them. But then you have to think about more heated complexity. Those are binary systems. So you need two massive stars in this case.
What are the comparative strengths of the two types of populations?
The compared to what?
The comparative strengths.
You mean
Are
brightness?
they all about the same brightness?
They're about the same brightness, yeah. They're close, yeah. The duration is different, however, which is the main distinguishing factor. So, let's talk a little bit more about the gamma ray burst supernova connection. And now we're going to go back, switch gears and focus back to the long duration gamma ray bursts, which we think we have strong evidence have to be associated with massive stellar death and black hole formation. So we do find all these type of gamma ray bursts in regions of massive young stars, which means that the locations of these things seem to be associated with places where big stars are born, which is also another hint that the stars that die are big and producing these events. And there's yet another implication about their origin. Now, in terms of their rates, I said before, they are rare. However, if you look throughout the entire sky, you will catch a lot of them. So, once every 10,000, 100,000 years in a typical galaxy is the number that we estimate, which is still, more, they're rare, but they're more frequent than typical supernovae, which is 100 times per galaxy on average. Now, again, remember, when I say rare in terms of how many we detect. But, as I said, there's 10,000 times more that are exploding than the ones we detect. So, in reality, you have a lot of gamma ray bursts, we just see a small portion of this, 10 to the 4, 10 to the 5, because they're very direct. Okay, so the most popular idea, that idea was proposed by a very popular scientist, Stanford Roosevelt. He's made a lot of public appearances and documentaries, and he's one of the forefathers, or one of the most highly impacted people in the gamma-ray burst supernova community at the University of California, Santa Cruz. He proposed that they represent the birth of a black hole in a collapse of a really massive star. Or, alternatively, if it's not a black hole, it has to be a highly magnetized neutron star, a magnetar. So what do we see exactly in terms of gamma-ray burst association with supernovae? And let's just focus on the optical luminosity, because after all, optical luminosity, we've been doing this, optical astronomy we've been doing for several hundred years. We have way more experience. We can do it from the ground. And we can observe things in the optical for way longer durations, in this case about 2 weeks, than what we can for the 30-second gamma-ray burst. So we know a 30-second gamma-ray burst takes over, but then what happens later is you see the afterglow, and occasionally you will see a little bump in the afterglow, in the optical radiation. And the question is, what is this bump? And if they are associated with type 1c supernova, you remember the light years have been showing you, the light goes up and it goes down, it reaches a peak. Maybe that bump is really associated with the peak of the type 1c supernova that's hidden, that follows the gamma-ray burst, or that's associated with the gamma-ray burst. So we do have a lot of early circumstantial evidence, including some observations, some hints that these are associated with supernovae. And this is how we see them with our telescope sometimes. We see this little bump in the afterglow, which could be the actual peak of the hidden type 1c supernova. And so you still have to have a core that collapses. The fact that the gamma-ray bursts are beamed explosions doesn't change the fact that you have a massive star that created an iron core, and it's the iron core that eventually collapses, produces a black hole or magnet star, and eventually explodes the star. But the process of collapse is way different, because now the collapse of the iron core itself is highly influenced by strong magnetic fields and rotation. And when you put those two very complicated things together, usually a joke that's going around the community when you go to conferences about supernovae and astrophysics in general, is that there's always going to be this one person in the room during Q&A that's going to ask the question, what about magnetic fields? You know, because nobody knows. It's such a complicated physics. So if you really want to put the speaker on the spot, you know, what about magnetic fields? Have you accounted for magnetic fields? So this is you know, a nasty way to make someone embarrassed. But the reality is that magnetic fields are important, and we're starting now to have enough computational power and algorithms and computer codes, including the flash code at the Flash Center, that can handle what happens when matter is highly magnetized and there's a strong degree of rotation. And it turns out that this seems to be the case for gamma-ray bursts. They always uniformly seem to be associated with strong rotation and magnetic fields. But for a long, as I said, that was circumstantial evidence. We still needed actual tangible proof of the gamma-ray burst supernova connection. And the tangible proof came in 2003 when we discovered GRB 0329, which was relatively nearby. Again, when I see the word nearby, I'm laughing because it's really 3 billion light years away. That's nearby. It was relatively bright, so it was an ideal target for us to study. And a week later, on the same location when GRB 0329 was discovered, the exact same spot, we found supernova 2003 DH. And we took a spectrum of it. And when I talked about supernova astrozoology, I said that the best way to figure out what supernova are, you have to take a spectrum and see what elements are involved in supernova. And when we did that, we see there was no hydrogen and helium in the spectrum. So that was a type 1c supernova. So the vast majority of all GRBs associated with supernova are associated with a specific type, which is also interesting. Why? Why preferentially gamma-ray bursts associate themselves with hydrogen poor, hydrogen helium poor type 1c supernova explosions? What's going on there? What's the link? And that would also have to do with rotation, because rotation can enhance, in many cases, the loss of mass from a star. a highly rotating star, imagine like taking a fluid and start really, really rapidly rotating it. It will start breaking apart in the outer layers. So slowly you can actually remove mass mechanically by rotation. Rotation aids mass loss. Therefore, that will explain the fact that those stars lose their hydrogen and helium anyway, at least partially. An alternative idea is that they could actually be members of binary systems. And those massive stars pile their companion stars with their hydrogen and helium layers. And then when they explode, they don't have those layers, and but they're rotating very fast as well. And it produces gamma ray bursts. So still a lot of things to think about and figure out about gamma ray bursts. But we finally have a very strong clue that those are supernova explosions, or related to supernova explosions, but with this unique degree of rotational magnetic fields. But you don't have it all the way around. We do have that all gamma ray bursts, or most gamma ray bursts we see are associated with type 1c supernova, but not all type 1c supernova are associated with gamma ray bursts. So if you do see 1c supernova, it's not necessarily that there was a gamma ray burst associated with it before the actual afterglow. So what's going on here? You know, again, it goes back to the fact that maybe you talk about binary versus single. Maybe some of these things happen in binary systems, where they bind up mass to a companion star, or whereas other systems are just a single massive star that takes place as a type 1c supernova, and it doesn't rotate very fast. Because now, rotation and binarity are related in a level. When you have a binary system, and you bring the system, the two stars together, the closer together they are, the more tightly locked they can transfer the rotation, the angular momentum, as we say in fancy words, of the system, of the entire system, to the individual stars. So you can spin the stars up by bringing them close together, as a massive binary evolves. You can spin the individual stars down. And that's where you can get a lot of rotation, magnetic fields, to produce gamma ray bursts that are associated with type 1c supernova. But when you have a single star, you don't have this extra enhancement of rotation.
So
yes?
when it's observed, the gamma ray burst is always first, and then the
Yes.
1c?
Yes.
And is this possibly because of shedding angular momentum, the way a neutron star, like a Crab nebula, energy is coming from decreases in rotational velocity? Could the gamma ray burst be something that caused a massive change in the spin?
Well, gamma ray burst itself, I mean, it's the cause of the effect scenario again. You have to have the spin and the collapse to get the gamma ray burst. But itself, once it happens and you have the energetic radiation produced from the central engine, which is the collapsed core of the star, black hole, neutron star.
So the burst is annihilation then?
It's just an energetic explosion, a radiation in gamma rays. But the burst lasts itself for 30 seconds, and those are the only 30 seconds that you can use to probe the central engine. Because everything that happens later in the afterglow, in the optical, is mostly associated with the expanding matter of the star. So yeah, so the first 30 seconds is what's related to the central engine. So it's a problem still debated. The current picture is that gamma ray bursts result from the collapse of a massive star. We're pretty sure about that. We're pretty sure that in most cases there's no hydrogen and helium associated with them, so associated with type 1c supernova. And they might be marking the formation of a black hole, because when a massive star collapses, it's either going to make a neutron star or a black hole. The most massive stars will more likely make black holes. And then you have rotation involved. The neutron star can wrap up its magnetic field that exists there before the explosion. Before the explosion, there's magnetic field there. But if the rotation is really fast, together with the collapse, it can wrap it up in ways that it can amplify and create a magnet, for example. So we really try to figure out whether really black holes has evolved. It's a really tough problem. But most people are convinced that that's the case for long duration gamma ray bursts. This is an animation of a collapsar by NASA. This is a very simple, this is a star. It's collapsing and producing gamma ray beam, all the radiation we get out here. This material here travels with speeds really close to the speed of light. The rest of the star explodes, This is a central engine that rotates very fast, producing those jets that happen to be direct towards the Earth. You will see the gamma ray bursts. If not, you will see either probably a deep supernova explosion. And as I said, they're very bright. Therefore, anytime you find something that's extremely bright in astrophysics, cosmologists get excited because they say, okay, those things are so bright, we're going to detect them at really far away distances, which means that you can find them at the very early stages of the universe, at the teenage universe. So when the universe was formed and you had the Big Bang, and you had matter collapsing to form galaxies and the first stars, eventually, people think they were really massive. And it goes back to the fact that the more massive a star is, the less it lives in terms of duration. So those first, or population 3, as we call them, stars, were very massive. In some cases, they collapsed and they produced a lot of primordial supernova explosions. And in some cases, they had a lot of rotation, magnetic fields, that produced primordial gamma ray bursts. Therefore, if we were able to observe these gamma ray bursts at really high distances, maybe we can infer something about the young universe, about the progress of the universe in terms of the first generation of stars and the condition of matter and radiation, but just by looking at these things, because you can put constraints. You can say, okay, the most distant gamma ray burst I've seen is 9 billion years away, which means that there can't be, there's stars that are born within the first 4 billion years of the universe's existence. So you can start trying to figure out when actually were the first galaxies and stars in the universe formed. And now you can put upper limits, just the further away you go by observing these gamma ray bursts. So before the universe cooled enough, after the explosion of the Big Bang, the inflation, the universe was very hot. It didn't allow for matter to combine, to produce things, because radiation was so energetic, it would break things apart all the time. It would break atoms all the time apart. But eventually, as the universe expanded and cooled down, matter was able to combine, recombine, and start producing atoms, and hydrogen and helium was there. Gravity started pulling things together, produced galaxies and stars. And that was the end of the Dark Ages. Before that was the Dark Ages, we call it Dark Ages because it was nothing, you couldn't see anything. So after the end of the Dark Ages, when you finally had matter coming together to form massive stars, that's when a lot of people are focusing their efforts using gamma ray bursts to study the properties of the universe. Because that's when you form the first stars, and that's when the first gamma ray bursts in the universe took place. And this is what this picture says to me. The further away we look into the universe, the Hubble Space Telescope, the further away towards the past we go. Obviously, there was a Big Bang. We can't see anything around here. This is the era dominated by radiation. And then you have the Dark Ages because you haven't yet combined matter to form stars. So you have no radiation. You had nothing shining in the universe for some time because you didn't have stars or galaxies. Eventually you did that, and you started forming the first stars and the first galaxies. And the first stars started blowing up, producing gamma ray bursts supernova, which we now see. So we can use gamma ray bursts to go that far back.
Stars formed before galaxies?
Huh?
Are you sure stars formed before galaxies?
Yes, you can have, you have gas. In some cases, those stars are supermassive. So we're talking about stars. People talk about stars that are 10,000, 50,000, 100,000, maybe 1 million times the mass of the sun. Those live very short times. Too obese. But yeah, you can have primordial stars and primordial galaxies.
Question?
Yes.
Have you talked about white holes at all? I know you a couple lectures.
About what?
White holes?
White?
Black holes and the counterpart?
Oh, no. White holes, no. This is not going to be...
Yeah, I don't want to get beyond.
No, we can talk in private if you want, but this is not material for this particular lecture series. But yeah, no, we're not going to talk about it in the main lectures, but if you want to talk about it, video.
Just origins, you know?
Yeah. So to summarize, today we talked about these very energetic gamma ray bursts, beam stellar explosions, A lot of them going on in the universe, we can only see a small percentage of them because they're highly directed and highly beamed, and we just have to happen to be in the way of this beam to be able to see them. The energy that's produced by gamma ray bursts is equivalent to about 1,000, 10,000 times of a typical supernova explosion, which means that if that was distributed uniformly, you would need to really convert the entire mass of the star into energy, which is not possible. Therefore, that points us to the conclusion that those are highly beamed explosions. We see two types based on how long those gamma ray durations, gamma ray burst duration lasts. Some of them are very, 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 very fast, less than 2 seconds, the short duration gamma ray bursts, while others last on average about 30 seconds or so, the long duration gamma ray bursts. And the two populations seem to come from different origins. We associate currently the long duration ones with the death of the massive rotating star, a collapsar, forming a black hole of a neutron star, while the short duration ones with potential mergers between neutron stars or neutron star and a black hole. So the jury is still out there to understand the fundamental properties of what happens when the beam is exploded. How is the magnetic field amplified when the core collapses with rotation? How are the jets born that accelerate matter to this velocity? All these are details that people are working on with very sophisticated three-dimensional magnetohydrodynamics, if you want me to use the fanciest word, codes, in order to be able to understand what's going on with special theory of relativity boiled in, which is an important part of these events. And they're very important for cosmology because they're so bright. You can find them really far away, really after the dark ages of the universe. We can actually probe the depths of the first stars that were born, the first population of stars that were born after the Big Bang. Thank you very much. Questions?
Yes.
All right. Okay. 1, 2. Yes.
What kind of detectors do they use for detect gamma rays?
They use gamma ray telescopes. So those are detectors that are sensitive just to the gamma rays. Kind of like if you go to the doctor and get X-ray.
I mean, is it the same as detecting X-rays?
It's similar. It's not the same because there's fewer gamma ray photons, so you need very high sensitivity to capture as many of them as possible. So it's very, very sensitive sensors. The technology is very complicated. It's material sciences. You have to do the right material to capture the photon, which then converts into electron. You really detect electrical signals at the end. You don't really see. This is very complicated engineering. Yeah.
Can you explain the mechanism when two stars rotate together? You say that they start accelerating or getting the rotation of individual stars faster. So if I understand that the tidal forces will keep the stars rotating according to their rotation around each other, so they will never exceed the rotation around
It will never exceed the rotation of the entire system, but the closer you get to this, the closer you bring the rotation to the entire system.
So they never set the limit of the rotation.
No, they don't, but it's still pretty fast. Yeah. Yes?
On the gamma ray burst jets, are they unidirectional or bidirectional? And if they're bidirectional, wouldn't that make a difference in the energy calculation?
Oh, well, we think we're pretty sure they're bidirectional. So you have a jet and a counter jet going in the exact opposite direction. And we have accounted for that in the energetics. Obviously, yeah. Yes? Well, let's, one second. Yes?
It doesn't seem that long ago that we used to hear that a gamma ray burst was being spotted about 340 to 350 times per year, almost one a day. Are you saying that our instrumentation is not actually detecting all of them? That maybe there are only 2 per day?
Oh, we're not detecting all of them because not all of them are directed towards the Earth.
I mean, from the standpoint of detectable ones.
Yeah. So sometimes we just don't find them. We don't look at the right place of the sky. You know. But if you do this for a long time and you measure over time how many you find in a certain portion of the sky, then you can deduce what the total rate is. So, you know, we do have the technology to find most of them, but we don't find all of them because we don't look at the right place. Some of them might be highly extinct. So there could be material in between us and the gamma ray bursts that absorbs a lot of radiation that we don't see. Yes?
Occasionally, you do mention Big Bang hypothesis on the work. A few years ago, the MIT journal or whatever it is issued a statement that, or published something that said that the Big Bang hypothesis or theory abandoned. May you enlighten us about that?
I haven't heard about this. I'm pretty sure the Big Bang is still dominant theory we have out there. It's been confirmed by a bunch of different projects experimentally. So we're pretty sure, in the scientific community right now, there's no debate whether there was a point in the time in the history of the universe, everything was packed together in a very, very small place, and everything started expanding. It's just reversing moving backwards. And we have confirmed this with different ways, not just one. Multiple ways point in the same direction. So I'm not aware of this person. I would love, if you can email me the link or you know, his paper or anything like that, I'd love to look at it.
Okay.
Thank you.
If I have the understanding.
Yeah, right. Any other questions? Yes?
I also heard that of course, we understand that if supernovas are within 10 light years of the Earth, they're going to kill all the light. But a gamma ray burst, if I remember right, if you're in the beam, I think the distance quoted was 3,500 light years. Is that correct?
Yeah, it's still galactic. So if it's in the galaxy, with the galaxy, it's about 300,000 light years across.
Okay.
So if it's in the galaxy and it happens to point directly towards the Earth, you might have a problem. The closer it is, the more problem you have. But yeah, but it's not going to happen. You can see.
It's a shooting gallery and we have the dark side.
It is. Yes.
I have another one of my simple questions. You're talking about billions of light years objects away from each other. Do we have any idea how far it is across the universe?
The gamma bursts or
No, in billions of light years.
Oh, I mean, the universe is 13.7 billion light years old, which means that ideally you could, you would want to look that far back. The reality is that you can't, because you can only see things after matter and radiation were decoupled. So when radiation was eventually free to stream out, which happened about 370,000, 400,000 years after the Big Bang, is when that happened. And the furthest away we can see in the universe is with a cosmic microwave background radiation. I can pull up a picture to show you, which shows the temperature variation of the primordial explosion that took place in the microwave. The microwave. So this is really lowest radiation. The temperature is about 3 Kelvin degrees. We're talking like almost absolute zero, really, really cold. And those little temperature variations, a little bit up, a little bit down, basically map out the initial distribution of matter in the universe, and where it was denser versus where it was less dense, and when the first things start to get together to make things. So I'll show you a picture of that if I have internet. I should. Okay. So this is the first picture of the universe. This is you can't see anything behind that. That's the birth picture of the cosmos. And we think the universe was about 400,000 years old after the Big Bang. Before that, radiation couldn't escape anything, so you couldn't see nothing. That's yeah. It was too hot. That's the infant universe. That's it.
Why isn't that for sale in tourist stores?
That should be. make a cool t-shirt. I'm thinking about being that for Halloween. You know? Any other questions? Yes?
Gamma rays redshifted the same way as any other radiation?
Sure.
Gamma rays what?
Redshifted.
Yeah, everything. Everything can be redshifted. So if those gamma ray bursts are far away, obviously, good point, the radiation is redshifted because the universe, the further away you are, the faster objects move away from you. So those things move away from the Earth at really high rates, thereby which is good for us astrophysicists, because not just the radiation is redshifted, but the time durations is delayed. So something that lasts a second around the Earth would last longer the further away you are because of the effects of special relativity. So that gives us more time to actually see things. Stretch out. Any other questions?
I have a question that probably is related, but when Maxwell determined the speed of light in his laboratory, he considered the permeability of space. How did he figure that out? And then permissivity. Those two things allow the magnetic fields that go with the photon and the electric field to combine with each other and produce this. How did he figure that out in the laboratory?
That's a good question. I need to go back and remember that piece of interesting science history. I don't actually remember. I do know that Maxwell was heavily theoretical as well. You know, the Maxwell equations for electromagnetism is the basis of modern electromagnetism. So yeah, it's. I think it was mainly pen and paper. It was mainly like thinking about the vacuum and how light travels around the kind of properties and how. But I'm not aware of the laboratory part of it, so I have to read up. You called me. Yeah. Yes.
In one of our discussions, you mentioned that Einstein added a mark on his formula.
Yeah, lambda.
The lambda.
Yeah.
And sort of, he kind of knew that it must be something like what we call dark energy now.
Yeah, and then he called
it was a mistake at the end.
Before he died, yeah, he called it the biggest mistake of his life. Turns out it wasn't. Yeah. Any other questions? All right, thank you very much.